So yesterday, section 5.3, exponential logarithmic equations, right? We solved the exponential logarithmic equation on pages 1 and 2, okay? Those on page 3, right, are on video. So you can watch, right? The video link is on OAKS, so you can watch the video at your leisure, right? I would try to work these yourself first, and then compare your answer to the video solution, okay? Instead of just watching the video and filling out your notes, right? Try to solve them first on your own. All right. And then we did example 2A, where we found the inverse function, okay, for that natural exponential function in 2A, or that function involving the natural exponential function in 2A. Okay. So now in 2B, we're going to find the inverse function for a function involving the natural log function. And then you'll have everything you need to successfully complete the WebAssign homework. So we have f of x is equal to the natural log of x plus 3 minus 1, right? So notice that the argument going to the natural log function is in parentheses, right? X plus 3 is the argument going into the natural log function. Okay. And this is a one-to-one function, so it has an inverse. And so we have the 4 basic steps, right, for finding an inverse. The first step is to replace f of x with y. So we have y is equal to the natural log of x plus 3 minus 1. And then we switch x and y. So we have x is equal to the natural log of y plus 3 minus 1. And then the third step, right, is solve for y. And so, solving for y, the first thing we do is add 1 to both sides. X plus 1 is equal to the natural log y plus 3. Okay. And now you know that y is part of the argument going into the natural log function. So we got to get rid of the ln. And so to get rid of the ln, right, the natural log, we can make, since the left side equals the right side, we can make the left side and the right side exponents on the number e. And we have e raised to the x plus 1 is equal to e raised to the natural log of y plus 3. And now on the right hand side, okay, you know the natural property for the natural log function. Right? The natural exponential function and the natural log function are inverse functions of each other. So they cancel each other, undo each other, and we're just left with the argument on the right hand side going into the natural log function. So the right hand side is just equal to y plus 3, right? A property for the natural log function. Okay. And now we can subtract 3 from both sides. Okay. And when I switch the left and right to two sides, I have y is equal to e raised to the x plus 1 minus 3. Okay. Sometimes it might prevent confusion if when you subtract you put the minus 3 in front of the exponential. That way you don't accidentally put the minus 3 up in the exponent. Okay. And then these right, and then you replace y with inverse function notation. have f inverse of x is equal to minus 3 plus e raised to x plus 1. Any questions on that? Now, we got to find the domain and range of the inverse function. Well, here's f of x, okay? And the domain of f of x, f of x is natural log x plus 3 minus 1, right? So this is f of x is just a transformation on the natural log function, right? You know the graph of the natural log function looks like this. Crosses the x-axis at the point 1, 0. Right? This is the graph of y equals the natural log of x, right? So f of x here is just a transformation on this graph, right? When we replace x with x plus 3, it shifts the entire graph to the left 3 units. And then when we subtract 1, shifts the graph down 1. So shifting the graph to the left 3 units and down 1 unit has no effect on the range. Okay? The range still goes from minus infinity to infinity. Right? There's no minimum y coordinate, no maximum. To find the domain, right, we have to set the argument going into the natural log function greater than 0. And when we solve that inequality, right, we get x is greater than negative 3. And so the domain of f of x in interval notation, parentheses minus 3, comma infinity. So the range of the inverse function equals the domain of f of x, right? So the range, right, it's the same set of numbers. So the range of the inverse function, right, is the numbers from all real numbers greater than minus 3. Right? These are the y values for the inverse function. Y greater than minus 3. The range of f of x, as I said, this is just a transformation on the graph of the natural log of x, right? Shifted to the left 3, down 1. The range still goes from minus infinity to plus infinity. No minimum y coordinate, no maximum y coordinate. So the domain of the inverse function equals the range of f of x, which is all real numbers. Any questions on that, ladies and gentlemen? Okay. So now you have everything you need to successfully complete the web assignment. So if you have your scientific calculator, you might want to get it out. So I get 6 copies. Anders, will you hand her one? Claudia, will you hand Hannah one? All right, so 5.4, okay, is on exponential and logarithmic model, okay. So before we talk about our basic model, the example one does not use the notation of our basic model. So let's do example one, and then we'll go back and talk about our basic model. So in example one, we're given the number of certain species of fish can be modeled by the formula or the function n of t is equal to 12 times e raised to 0.012 p power, where t is measured in years and n of t is measured in millions. Okay? So n of t tells us how many fish there are at time t. Okay? This is an example of an exponential growth model. And you see the natural exponential function e. In A, you're asked, what is the relative rate of growth of the fish population? So we have n of t, the number of fish at time t is equal to 12 times e raised to 0.012 t power. What is the relative rate of growth of the fish population? That is the number in front of the t and the exponent on the number e. So the relative growth rate, okay, is 0.012, and we can write that as a percentage. Let's change the decimal to a percentage, move the decimal place over 2 spaces, and then add percentage symbols, okay? So the relative growth rate, and since t is in years, the relative growth rate is 1.2% per year. So that number in front of the t, right, is the relative growth rate. In B, it asks, what will the fish population be after 15 years? Well, to find the fish population after 15 years, you just put 15 in for t, right, because t is years. So we have n of 15 is equal to 12 times e raised to 0.012 times 15 power. And 0.012 times 15 is equal to 0.18. Now, if this question is on the final exam, okay, or the exam next week, you don't have a calculator, right? So when you answer this question, either on the final exam or on the exam next week, you have to stop right here. Okay? do that calculation. You don't have a calculator. Okay, you can't get specific. Okay. Now, if you have your scientific calculator out, there's an e to the x key. You should have an e to the x key on your calculator, and you put in 0.18 in for x, right? And evaluating e to the 0.18, and you should get a number equal to 1. Now I'm going to write this out to several decimal places, right? You don't have this number in your display. 1.1 972 17363. When you evaluate e to the 0.18, right, in your calculator, hit enter, you should get a number 1.1972, right, in your display. Now we multiply that number by 12. And when you multiply that number by 12, you get 14 to 3 decimal places, 14.367. Now WebAssign will tell you how many decimal places to give your answer. So when you're doing the calculations on your calculator, right, do the calculations in several decimal places, right? Just leave the number in the display until your final answer. And so, how many fish after 15 years? Number of fish is 14.367, but remember, N of T is in millions. So this is the number of million fish. 14.367 million fish, okay? And so this is like the answer you would type into WebAssign. Okay. Yes, ma'am. Say that again.
For the exponential multiplication, I didn't get 0.001.
What'd you get? 0.012 times 15. That should move the, just multiply by 10 should have moved the decimal place over to the right one, right? So I'm going to double check your math. Everybody else get 0.18? Right. All right. So that's sort of a nice introduction to exponential growth models. Okay. Now, on your back, the very last page is blank. Okay. So I'd like you to flip over to the blank page because I'm going to put some stuff on the make some comments about our model, right, at the top of page 1. One thing that's kind of you got to keep in mind, right, like on the final, right, the model from these notes, right, is of the form A of T is equal to A sub 0 times E to the KT power. But in WebAssign, instead of using A, I think they use the letter P, right? And I think on the final exam, we use this notation, right, the letter A. But, you know, it doesn't have to be, right? This could be the letter P, right, or the letter F, or anything else, okay? Capital N, right? But this is the basic form of the model, okay? So, at t equals 0, right? At t, when we evaluate this function at t equals 0, right? In the exponent on the number e, we have k times 0, which is 0, and e to the 0 is 1. And so the right-hand side is equals a sub 0 times 1, which is a sub 0. Okay? And a sub 0 is the initial amount of a substance or population. The K here, okay, which was in our example from page 1, was 0.012. K is equal to the growth rate if it's greater than 0. If it's positive, in our example we just did, it was positive, right? So it's the growth rate. It's called the decay rate if it's less than 0, if it's negative. So we have substances that increase over time, and we have substances that decrease over time. We are interested at times, the time for a population to double in size. So if A sub 0 is our initial amount, right? We're interested in the time for a population to go from the initial amount, A0, to twice that amount, right? That's what we mean by time for a population to double. The formula, capital T, is the time for the population to double, okay? Is equal to the natural log of 2, the number 2, divided by the growth rate K. Okay? And sometimes you're given the time it takes for the population to double, and you got to find the growth rate. So if you solve this equation for K, you get the growth rate K is equal to the natural log of 2 divided by the time it takes for the population to double. So this is, you can find the value of K given the time for the population to double in size. Similarly, we're often given the time for a substance to decay in half. Okay. In this case, right, that's the time for the substance to go from the initial amount, A0, to 1/2 its size. Decay means the quantity of substances get less, get smaller. Okay. That time, capital T, okay, is equal to the natural log of 1/2 over the decay rate K. And using the properties of the natural log function, right, the quotient rule, T can be written as, right, 1/2, let's do it this way, 1/2, right, can be written as the decimal 0.5. Okay. natural log of 1/2 by the quotient is the natural log of 1 minus the natural log of 2, and the natural log of 1 is 0. So this can also be written as minus the natural log of 2 over k. And you notice, right, it looks like this over here, except with a minus sign. So the time for a substance to decay in half, capital T, right? The numerator, right? The natural log of 1/2, the natural log of 0.5, and minus the natural log of 2 all have the same decimal value. And now similarly, sometimes we're given the time for a substance to decay in half, and we gotta find the decay rate. So when you solve for K, you get K is equal to the natural log of 0.5 divided by the time for the substance to decay in half, or on the bottom down here, right? K is equal to minus the natural log of 2. Okay. So this is given the time to decay in half, okay, for a substance. Okay. Does this make sense? All right, I'm just giving you the formula, so we're not grinding. I'm not going to prove it. Okay, you read it as textbook if you want to prove it. Okay. All right. So now let's take a look at example 2. A bacteria culture starts with 500 bacteria, and 5 hours later has 4,000 bacteria. So in part A, it says find an expression for the number of bacteria after T hours. So our model is the number of bacteria, right, after T hours is equal to the initial number, A0, times E to the KP power. This is our math model. Now, the initial number is the number at T equals 0, which we know is A sub 0, right? Because we put in 0 for T up here. 0 times K is 0, and E to the 0 is 1. And so the initial number, right, at time T equals 0 is A0, and we're told that's 500, right? A bacteria culture starts with 500 bacteria. Okay? So that's the initial number of bacteria. Okay? So we can put 500 in for A0 up here. And our model is A of T is equal to 500 times E to the KT power. Now all we got to do is find the growth rate. Okay. Well, we're told that the number of bacteria after 5 hours is 4,000. A of 5 is equal to 4,000. Number of bacteria after 5 hours. So when I put 5 in for T up here, okay, in our model, I have A of 5 is equal to 500 times E to the K times 5 power, right? But A of 5 the number of bacteria, right? A of 5 is the number of bacteria at T equals 5, and A of 5 is equal to 4,000. So I have 4,000 is equal to 500 times E. Now I'm going to write that as to the 5K power. We got to solve for K. To get the growth rate. Well, this is 500 times E to the 5K, right? So division undoes multiplication. So we divide both sides by 500. We have 4,000 over 500 is equal to 500 times E to the KT power over 500. 4,000 over 500 is equal to 8. 500's cancel. We have 8 is equal to E raised to the KT power. Well, K is in the exponent on the number E, right? We got to get rid of the number E. So we used property 3 from the natural log function, right? The natural log of E to the x is just the exponent x. So if we take the natural log of both sides, the right-hand side will just equal K times T. We have the natural log of 8 is equal to the natural log of E to the KT power. And so by property 3, right, the natural log function, the right-hand side is just equal to K. Oh, what did I do wrong? It's supposed to be 5K. Thank you. This is supposed to be 5K. This is supposed to be 5K. This is supposed to be 5K. One of the problems I have teaching this early in the morning is the caffeine hasn't kicked in. At 1 o'clock in my 1 o'clock afternoon class, man, I'm fine. But this time in the morning, right, I'm still waiting for the caffeine. So, thank you. Okay. So, right, so at this step, right, we have 4,000 is equal to 500 times E to the 5K. You divide both sides by 500, get 8 is equal to E to the 5K. Now we take the natural log of both sides. We get the natural log of 8 is equal to the natural log of E to the 5K. So by property 3, this on the right-hand side is just 5K. And now I divide both sides by 5, switch the two sides, and I get K, the growth rate, is equal to the natural log of 8 over 5. Now, you don't have a calculator on the exam 4 or the final exam, right? So this is the growth rate, right? On exam 4 and the final exam. So we're finding an expression for the number of bacteria after T hours. So now we can put K in, that value in for K in our model over here. Okay. Now, in WebAssign, you gotta type in a decimal, right? So using your calculator, the natural log of 8 divided by 5 is equal to 0.4159. So now we substitute in for K in our model, and we have A of T is equal to 500 times E. Now K in this case right on the exam, K is the natural log of 8 over 5. Natural log of 8 over 5 times T. That's the model for part A, okay, for the exam. For WebAssign, what's in parentheses is 0.4159. So for WebAssign, we have 500 times E raised to 0.4159 times T. Okay. Now you notice that E doesn't cancel the natural log function because this is an E raised to the natural log of something, right? The natural log of 8 is in this fraction that's being multiplied by T. So the E and the ln don't cancel. Are we cool? Is everything okay? So in part B, right? So this is A, part A, okay? Answer to part A. Okay. In part B, it says find the number of bacteria that will be present after 6 hours. So how do we find that? We just put 6 in for T, right? So A of 6, so this is part B. So A of 6 on the exam is equal to 500 times E raised to the natural log of 8 over 5 times 6. Okay. And you can, if you want to, you can write this as 6/5 times the natural log of 8 and other stuff. Right? But that's the exact answer. Okay. For WebAssign, A of 6 is equal to 500 times E raised to 0.4159 times 6, right? So we put 6 in for T here for WebAssign and 6 in for T up here for the exam. Okay. And 0.4159 times 6 in the exponent I got is equal to 2.4954. So when you multiply E raised to the 2.4954 power by 500 and round to the whole integer, right? Because you can't have a fraction of a bacteria. Okay? You get 6,063 bacteria after 6 hours. So this is the answer, right? If this was an exam question, and this is the answer for WebAssign. Are you with me? Okay. C, it says, when will the population reach 15,000? Okay. So here's our models. In C, right, we gotta solve for T, right, little t. When will the population reach 15,000, right? So you replace A of T with 15,000, right? At some point, the number of bacteria is going to be 15,000. What's the value of T? Okay. So we have 15,000 is equal to 500 times E raised to the, I'm just going to do the WebAssign version, 0.4159 T power. And now you divide both sides by 500. And 15,000 divided by 500 is 30. And now to T's in the exponent number E, right? So to get rid of E, we gotta take the natural log of both sides, right? So we're using property 3 again. And we have the natural log of 30 is equal to the natural log of E raised to 0.4159 T power. So on the left, we have the natural log of 30, and on the right, we have 0.4159 times T. And now, right, this is just a product on the right-hand side, so you divide both sides by 0.4159. When we switch two sides, you get T. The time for the number of bacteria to grow to 15,000 is the natural log of 30 divided by 0.4159, which is the growth rate. Oh. Not done. Right, this got to go in WebAssign, right? WebAssign wants a number. So use your calculator, right? Punch in natural log of 30, divide by 0.4159, and you get 8, right? For one decimal place, you get 8.2 hours. Remember, T is in hours, okay? So it takes 8.2 hours for the number of the bacteria to go from 500 to 15,000. Okay. Cool beans? Okay. All right, so let's take a look at example 3. And that one talks about the half-life of a radioactive element. Top of the page. The half-life of a radioactive element is the time required for half of the radioactive nuclei present in a sample to decay. Right? And that's what we talked about that. Right? You got that written on page 4, the last page of your handout. Right? By the half-life. So carbon-14, one of the 3 isotopes of carbon, has a half-life of 5,730 years. It takes 5,730 years for a given amount of carbon-14 to decay to 1/2 its original size. if 10 grams were present originally, how much will be left after 2,000 years? So on the last page, right, I gave you the formula for the time for substance to decay in half. And using that formula, we wrote out the decay rate, okay? K is equal to log of 0.5 divided by the time it takes for substance to decay in half, right? It's on the, you wrote it down off the board, that's what you got. Well, 0.5 is equal to log of 0.5 is equal to minus 0.6931. Now with WebAssign, sometimes, right, you gotta write these, you gotta have these numbers up several decimal places, so that's why you wanna use your memory and your calculator display. 0.693147,181, and 5,730 years is the time it takes for the substance to decay in half, right? So when you do that division, you get minus 0.000000097 as the decay rate. We're given that the initial amount of the substance, the initial amount of carbon is 10 grams, right? That's the initial amount. So our decay rate model, A of t, right, is equal to A sub 0 times e to the kt power. A sub 0 is 10, and k is minus 0.000012097 times t. So the exponent's negative, right? There's minus sign in front of the decay rate. So you know this is exponential decay. So in A, we're asked if 10 grams were present originally, how much will be left after 2,000 years? Well, that's A of 2,000. So we put 2,000 in for T. We have A of 2,000 is equal to 10 times E to the minus 0.0001297 times 2,000 power. So when you multiply the decay rate times 2,000, okay, you get minus 0.24194. So E raised to this number, using your calculator, is equal to 0.785. And then when you multiply 0.785 by 10, you get 7.85 years. Two decimal places.
That's supposed to be grams.
And that is supposed to be grams. Okay. Where did I see years? Oh, I was looking at B. Thank you. Yeah, that's supposed to be grams. So the amount it 10 grams were present originally. How much we left after 2,000 years? 7.85 grams. In B, it says, when will there be 2 grams left? So to find the time it takes when there be 2 grams left, you put 2 in for A of T and solve for T. So we have 2 is equal to 10 times E to the minus 0.000120097 T power. You divide both sides by 10, you get 0.2 is equal to E raised to the minus 0.000120097 T power. And now to get rid of the E, you know, you gotta take the natural log of both sides, right? So we have the natural log of 2, 0.2 is equal to the natural log of the right-hand side, which is minus 0.000120097 T. Right? I just skipped a step. And now when you divide both sides by the decay rate, you get the time, T. T is equal to the natural log of 0.2 over minus 0.000120097. Using your calculator, the time it takes for decay from 10 grams to 2 grams is 13,304 years, 304.4 years. So it takes a long time for carbon to decay. So we did 2 exponential growth problems and 1 exponential decay problem. So we'll do more tomorrow. So we will finish this tomorrow, and then the homework will be due actually Thursday night, but there's only 6 problems. Okay, it's hard to find good problems on this section in WebAssign.